This is going to be a short lecture to look at just a few remaining things to finish off the AVEngine project. You probably noticed that there's going to be a new due date for that. The due date is now going to be Tuesday next week. You're going to do presentations, and that's all we're going to do in classes. You'll just do, you'll present your code to me. Then next Thursday, what we'll do is we'll start on audio units. Alright, writing custom audio units that can be inserts for any DAW on an iPhone or iPad. So for this lecture, we're going to do a quick recap of doing Fourier transforms using the vDSP library. We're going to look at doing BIQUADs using the vDSP. And we're just going to look at that one flavor of filters. It's an easy one to implement and I think understand, but really there's several flavors of filters that you could use, and they all work kind of similarly. So once you understand BIQUAD, then you can go through and learn any of them really. And then we're going to look at audio sessions and look at how that's used inside the AVEngine. And so then we will have covered everything related to this AVEngine, from FFT to the audio sessions to the viewer, and also setting up the effects chains and modifying the effects parameters. Alright, so I added this diagram to the PowerPoint. I just committed it just a moment ago, so you can see a few changes here. So take a look at this. Well, let me take one step back. Look at the notes here. The Fourier transforms. What was step 1? Create a weights array of twiddle factors. Okay, using vDSP create FFT setup right here. Okay. So where did we come across that in the code? We did that in the start audio player with file. So all this is audio session stuff. Alright. So we've loaded in the file, started up the engine, created and attached our effects. Now we're doing the FFT setup. These are those twiddle factors. Okay. So the first thing we need to figure out is what is our FFT order. So this is a log 2 of your window size. We had selected a window size of 1024. So that means our log order will be 10. This self.in is assigned when someone does a init with buffer size. Okay, you see that's passed in, and then we override in. We made in read only here in the made it read only right here. So that's in the header file, the interface in the header file. So there's no setter, so we can't do self.in because that function doesn't exist. So we're going to directly access the IVAR. And anytime this buffer size changes, what else are we going to change? The FFT magnitudes. Okay, we're going to clear them out and give them a new size. Okay. Alright, so let's pop down here. So we've got our FFT order, and just like I showed in the notes, we're going to call vDSP create FFT setup. So we pass it the order as well as the type of FFT that we want to do. Apple supports 3 types of FFT, either radix 2, radix 3, or radix 5. If you want to read about the radix algorithms, I don't teach that in 502. We do just the DFT. So if you're interested in what makes the FFT different from the DFT, this is a really good resource. You can open up that link, and they go over the different types of radix algorithms. And there's more than just 2, 3, and 5, but those are the ones that Apple supports. Okay. So we've got our FFT settings, and then we're going to make a home for our FFT data. Now let's look over here. What is FFT data? It's this variable right here. You see that? FFT data. It is a split buffer array. This is actually a C type, so it's not an NS object. It's actually a pointer to a struct of 2 pointers. And those 2 pointers go to arrays, dynamically allocated. So these are sitting on the heap. Dynamically allocated arrays of length n over 2. It's going to be real part and the imaginary part. Or actually, it can also contain the even indices and the odd indices for our real data, and real and imaginary for the complex data. So we're going to go ahead and allocate some space for that. Alright, so we're going to take this pointer and we're going to say, here's the pointer to the real portion, and it's a float pointer. We're running a malloc, an array. How big does the array need to be? Well, it needs to be at least the size of float, so that would give us 1 element, but we don't want 1 element, we want, look right here, n over 2 elements for the real part, and also n over 2 elements for the imaginary part. So we're grabbing our buffer size over 2, we're going to allocate all that space. Okay. I mentioned briefly in class why we have this underscore here. This is related to the fact that FFT data is a C type, so you can actually see, I mean, we're doing a float pointer with malloc. That's, that is not the syntax we use in Objective-C. So this is a C type array, and we didn't have to put it in a property. I like to put things in a property. We didn't have to do this, but since I did put it in a property, and it has this type complex split, which basically just defines a pointer, like I said, a pointer to a struct with two members that each points to arrays. So this is a C type. So there's no concept of encapsulation in C. So there's no setter that's appropriate for this. Objective-C does not know how to interpret that. So if we put self dot, it's going to complain. It says expression is not assignable. It does not know what to do with that data type. But since we define it as a property, it's still, that IVAR is going to be automatically synthesized when we compile. So it does exist, so we're going to access it directly. And this is the typical procedure for encapsulating primitives, well, maybe not primitives, but at least C types and dynamically allocated arrays. So this is not an uncommon practice. Okay, so we've created this FFT data, right? And what else have we created? We've created this FFT settings, right? Right up here. Oh, where was it? I lost it. Here it is. Oh, right above. FFT settings. So the next thing we're going to do, we have FFT data, FFT settings. Let's make a window, all right, and a windowed buffer. So first we're going to make some space for a Hamming window. It needs to be size n. Why? Because we're multiplying everything inside our buffer by our window. So same thing, it's going to be a float pointer. We're going to allocate space, size n. We're going to save it in a property called Hamming window. Okay, so in this case it is a primitive type, so I wasn't exactly sure. Objective-C does know how to handle primitives. Okay, so we can do a self.Hamming window, and that's going to go through a setter, and Objective-C can't handle that. And then what we're going to do is right now there's no values. It's not even 0. It's actually just space, and there could be garbage data in there. So we want to go ahead and assign values that are appropriate for a window. Now, if you want to clear out and ensure that it's going to be 0, use calloc instead. Okay, calloc is a clear allocate. So we've made some space. We're going to pass that buffer in here into vDSP ham window. Okay, we're telling it its length n. Since it's a C type, there's no way that this pointer knows how long the array is. We have to keep track of that manually. Alright, so we pass that in. So now we have our static hamming window. I'm calling it static because this shouldn't be changing until we change the window size. Okay. And last but not least, let's allocate some space for our windowed buffer. What's our windowed buffer? Well, it's our audio here times our window. We multiply those two together. We're going to save it inside our windowed buffer. So we'll just allocate some space for that. Right there. Also length n. Okay. I'm installing the tap on the distortion node. Alright. It's going to be, we're requesting a buffer size of length n. This file, with this processing format, or this AV audio format. And in our completion block, what do we get? We get access to a pointer of AV audio PCM buffer, and we get a pointer to an AV audio time. So for this example, all we're going to look at is the buffer. We're going to ignore the time. So before we do anything, we just make sure that there's something there. If this is a nil pointer, then we're going to just return out. But assuming there's something there, what are we going to do? First, we're going to take our window, multiply it by our audio buffer. So we're going to use vDSP vmul. This is a process that's happening out of place, so we need to also give it a buffer to return to. So we're going to pass in a float array. Right? This is what we get from the DAW. Stride length of 1. We're going to pass in our window. That's what we're multiplying the audio by. Stride length of 1. And we're going to return this in a windowed buffer. Stride length of 1. And all of these arrays have a length of n. So now we have windowed buffer. What's the next step? Is to split that up. So all we need to do is pass this through the C to Z function. Alright. So we're going to do a typecast here. We're gonna take windowed buffer, and we're gonna tell this function vDSP C to Z that this is actually a pointer to a complex type. All right. It doesn't know any better. That's kind of one of the dangerous things, but one of the nice things about C is you can switch types just by typecasting. So we're gonna trick this function into thinking that this is complex data. And we're gonna say it's a stride length of 2, so that when we split this up, it's gonna take every other element starting at the 0th index and starting at the 1st index, and it's gonna pop it where? Inside our FFT data. Okay. So it's gonna take the C to Z and it's gonna put it inside FFT data. Here I'm saying one is real type and one's imaginary type. That's for after it's actually gone through the transformation. This is prior to the transformation, so when we load it up, it's actually going to be even and odd. And we're doing a forward FFT, right? We're going into the frequency domain. And again, we saved this log2n. This is the FFT order. So it should be 10 in this case, for an n of 1024. Whoops, jumped ahead. I'm sorry. We had just finished up C to Z, so then we pass in this FFT data down here into the FFT ZRIP. ZRIP means it's going to be a split buffer, and this is real data that we're passing in, and it's in-place processing. So it's going to clobber everything that was in FFT data, and now it's going to put real and imaginary data in there. Okay. Our stride length changes to 1. Why is that? Well, since this is a split buffer, each element corresponds to a different frequency element. If we were to go the opposite direction, if we were to do a Z to C, then it would go real, imaginary, real, imaginary, real, imaginary. So to iterate over sequential frequency bins, it would be a stride length of 2. Right? But this is not complex array, it's a split array, so stride length of 1. One thing I left out, actually, when we went over this in class last time, is we need to scale by n. So I'll let you add that yourself. You need to do a vector multiply by a scalar. You can look that up. It's a function. It's a vDSP function. And you need to take you can either do it to the FFT data or you can do it to the mags data. It doesn't matter where you scale. You can move the scale down here if you want. Oops. You can put it there. Okay. So in addition to scaling, the last thing we want to do is grab the absolute value. Right? vDSP, z, meaning it's a split buffer. It's a vector. We're doing the absolute value. So we're passing it in. This is out-of-place processing, so we're going to save this in a separate array. We've already designated space for that. It's FFT mags. Let's look over here. One important thing I want to point out with this FFT data, look at this FFT function. This is our zrip function. Look at that arrow. It goes both ways, right? We pass in FFT, it operates on it, and it puts it back in that same place. So once we have that, we take the absolute value, and now we save it in FFT mags, which is real again, because the absolute value of a complex array is a real array. Okay. So moving on. Now you have your FFT magnitudes here, that then you're going to implement up here in your FFT UE viewer, right? You're going to be grabbing a magnitude from the current bin. It's exactly what you're grabbing from. Self dot right? Okay. So the last thing we're going to look at, oh no, two more things. I asked you to implement a BIQUAD. We didn't really go over it yet, but now you'll have time. We'll go over it now. vDSP BIQUAD. I guess I can enlarge this. So vDSP BIQUAD is a single channel cascaded, we have a cascaded array of individual IIR sections. So in this case, we're looking at just a single section, right? We have 3 feed-forward state variables or gains with 2 states, and 2 feedback coefficients with 2 states, and those get summed together for a total output y, right? But we can have as many of these together as we want. That's really great for example, a parametric EQ. You could set up a parametric EQ with as many bands as you want, and you can make each band just an individual IIR section. So you can have one section take care of each band and cascade those together. And this is implemented in direct form 1, which is the way that I teach it in 502, if you've taken that. So just like the FFT, we're going to create a setup first. This is something you should do anytime you set or reset your buffer size, most likely. It takes in arguments. It needs to know how many sections there are, and it wants to know what the gain values of your coefficients are. We're going to look at single channel, but in multi-channel, you also pass in the number of channels. And those are actually done in direct form 2, which is a transformation of direct form 1. They are functionally equivalent, but direct form 2 has 1 fewer state. Oh, actually, in this case, it's going to have 2 fewer states. We do not cover the direct form 1 to direct form 2 transformation in 502, so if that's confusing to you, that's alright, you can read about it. It's not hugely important though. Okay, so the create setup function is going to return a setup object, and we're going to pass that into the filter every time we want to execute the filter. And the setup can be called repeatedly. So we're going to go ahead and make this a property and just save it to, the object, our class here. And we're going to make it atomic so that as it's being passed into a function for execution, it can't be simultaneously changed and it's by another call. All right, so we're going to make it atomic, so it can only be accessed by one accessor at a time. So what we're going to have to do, since we're passing in this setup, the coefficients, is we need to make some space for coefficients. We know there's going to be 5, 3 feed forward and 2 feedbacks. Okay, so we're going to make a 5-element array per section, but we're only going to have one section here, so we'll just have 5 coefficients to deal with. But you know how to calculate these. You made an EQ calculator that gives you values for B0, B1, B2, A1, and A2, which is great. So when you're ready to assign the coefficients, the easiest thing to do might be just to iterate over your number of sections. So in our case, so this is the generic case where you don't know how many sections there are. For our case, there's just one section, so you could drop the for loop altogether if you want and just directly assign coefficients of 0, 1, 2, 3, 4, and 5. And you pass in your B0 and B2, A1, A2. That's the order it has to be in. Do not mess up the order or your filter is going to sound bad. These are the coefficients you calculate with your EQ calculator. Now, moving on to the execution. So this is what's going to happen in your, for example, in your tap that you install. So it needs to know this setup object with all of your filter coefficients, and it's going to want pointers to the input as well as the output. So this is out of place processing. All right, we have a separate output buffer from our input buffer. It's also going to want to know the stride. In our case, this is going to be 1. We're operating on real data, single channel. The other thing that you need to control or take control of are the states. Here we're calling them delay values. But this is just your state memory. You need to store that. Okay, this the BIQUAD is not going to store that for you. So we're going to keep an array of floats of previous delay values, right? Or previous state values for each section. And this array is going to update with new values, and the filter is going to, all we have to do is give the filter a pointer to these states, and the filter will update the values itself, right? But we have to be responsible for hanging on to it. And we also have to tell the filter how many samples it should be expecting to process. So, this is this is a pretty big hint for your project. If we wanted to set up delays, for example, for one single section, how many do we need? Right? How many do we have here? For direct form 1, we've got 1, 2, 3, 4. 4 states. So we'll make an array called a float array called delays, and it'll have 4 elements, and we'll initialize it to just zeros. That's how you should always initialize your states. Now we also need to create a coefficient array, right? We're going to have 5 coefficients times the number of sections. In this case, we're going to have just one section, so we'll have 5 elements. What's the ordering of it? B0, B1, B2, A1, A2. All right. You know these already because there should be some default cutoff and Q factor, that the filter initializes with when it loads up. So whatever coefficients come out of that default state, that's what you should load up for the initial settings for your coefficients. And then we have everything we need to set up our BIQUAD object. So what's the type? The type is vDSP BIQUAD setup. The object name we're just calling setup. And that equals the output of this function. Moving on. So we pass our filter coefficients into this vDSP BIQUAD create setup, store in an object called setup. Then, when you're ready to filter, you have your setup object, your delays of all of your previous states. You need to make an input and an output array. Right? These should be float arrays. And your number of frames. In this case, our number of frames is going to be 1. Alright. And then, once you're all done, this would happen maybe in your deconstructor or when you're exiting the program, you're going to call vDSP BIQUAD destroy setup.
Daddy,
Okay, last topic for us to cover, AV audio sessions. So what's an AV audio session? An AV audio session is a controller that's owned by iOS, and it handles all of the audio for all of the apps that are open on your phone. You can think, you can imagine a case where there's lots of audio that wants to happen at the same time. Maybe there's a music app that's playing in the background. Maybe you have a game in the foreground with some sound effects. Maybe you have a phone call coming in. This could all be happening simultaneously. So, rather than having a free-for-all chaos, iOS is the ultimate decider of who gets to be heard by the listener. Now, each app can make requests based on its individual needs, but those requests are not always honored 100% of the time. So, some other examples of how audio might be interacted with in the context of the operating system or other apps that are open. How is your app going to be affected by a ring, if the phone rings? Or how's your app going to be affected when someone flips the silent switch? Should other apps' music or sounds stop when your app's audio starts? Or should it go over top of background audio? And should your audio duck when the phone rings? Or what happens when someone docks their device? These are all questions that Apple has no idea. These are all questions that you answer and you provide by registering with the AV audio session. There's one audio session for the whole phone, and every app registers with it. So as much information as you can fill out, your app will perform better and better according to your specifications. So the AV audio session allows you to set up input and output routing for your app, determine how other apps' audio is mixed with yours, and handle interruptions, audio interruptions from other apps. Now there are 7 broad categories that exist for typical audio behavior, but only one of these categories has both audio playback and recording. So that's going to be the one, we'll cover it in some detail later. There's one category that, where were we? There's one category that allows for playback and recording. That's the one we're going to use. So an audio session is a singleton owned by iOS. Now, if you recall from the very first lecture, we talked about design patterns, and throughout this course we've talked about a couple different design patterns like encapsulation and model view controller, architecture, and the idea of using a create method. That's actually wrapping up your alloc init into a creator, or sometimes called a constructor. That's part of a design pattern as well. So a singleton is a type of design pattern. A singleton is when a creator can be called many times by many different people, or many different functions, whatever, but there's only one object that lives in memory. And anytime a new function or a new class calls the creator, it doesn't spin off a new version of that class, it doesn't spin off a new object, it just gives you a pointer to the one and only instance that was created. Okay? So in this case, the first function to create an AV audio session, which will actually be the OS as it's booting up. So the OS itself creates an AV audio session. There's one instance of that session. Every other app that calls this shared instance, this is a creator on AV audio session, is returned a pointer that is a pointer to the existing session that is already created. So that's how this one session can know about all of the audio needs from all of the apps. So useful for coordinating actions across the system. So if you don't make a call to session, the default category of behavior is what's called the AV audio session category solo ambient, and that's not really amenable to audio recording and playback. It does have playback enabled, but recording is disabled. The silent switch by default will turn off the audio. When the screen is locked, by default the audio will be silenced. Okay, and your audio sends a silence message to any other apps with audio. So this is the default behavior if you don't make any overrides with the AV audio session. This is a silly little cartoon from the textbook. It shows, for example, let's say you have a music app that's currently in the foreground, and the user is starting to launch up your telephone app called Speak Here in this example. Speak Here is going to register with the AV audio session and say that it wants to take control over the foreground audio, right? Once it becomes activated. So what does Core Audio do? It says it sends a message to this music app saying it needs to be deactivated. All right. So anything the music app wants to take care of, like pausing the audio nicely, saving the time where the audio was paused, anything else like that, that needs to be done in a callback function. All right, when the deactivation is made. Then Core Audio is going to send a notification to your app saying that it is now activated. So you know the moment that happens, and so you can start your audio up with confidence that you won't be interrupted. So when you're ready to start playing audio, you should activate your session. So it's a really easy thing to do. Once you've made, going back to this, once we've made our session, and we're ready to start playing audio, we pass it this selector, set active. We pass in the argument yes or true. You can say true now. If there's a problem or if there's a conflict, that will be passed back as an error message. All right. And then if it comes back as false, we can handle that error. All right. And when you're ready to deactivate, same thing. Instead of passing yes to set active, you pass no. And that lets other apps know that they can, resume their audio. Okay. Another thing that you can set is the secondary audio should be silenced hint. It's called a hint because it's not a directive, right? You can tell iOS that you prefer that other audio be silenced when your audio is playing. It won't happen 100%. May not happen 100% of the time, but you can at least request it to give the user. iOS wants to give the user the best user experience. They really do. So you should take advantage of using the session fully, the AV audio session, so that your app acts nicely with all the other apps. Now I had mentioned a few different categories. The bottom one there that's highlighted in gray, that's the default one. We already talked about that one. You can go through this table. You can just pause this video and look at the different categories if you're interested. The one that I recommend, just as a general rule of thumb, is the AV audio session play and record. It's highlighted with the red box here. Under this category, your audio is not silenced by the silent switch. It does allow for input and output, so you can record and playback. And by default, it will interrupt non-mixable audio apps, but you can actually change this setting. So you have this is what's going to be your best category for most of your audio applications. And once the session is created, we can set its category very simply. Again, we're going to return a bool of whether this succeeded or not. We're going to pass the session object a message or selector called set category. We want to pass in the category that we want to use. Here we're going to use the play and record category, and if there's any conflicts, we'll get an error message. Okay, so responding to interruptions. So you can imagine a scenario like this where a phone or an alarm, something that's going to take priority, is going to clobber your audio. So whether you like it or not, iOS or Core Audio may end your audio stream. So the best thing to do is just accept that fact and fill out the interruptions so that you can at least handle those interruptions in a nice way. So let's say your audio session becomes active. That's what's starting here at number 1. And then some sort of higher priority audio is going to happen. For example, a phone call audio session. So when that happens, the phone says first that it wants to take active section. So you get a notification that you're about to lose your active session. Then the phone call does take the active session, and then you get deactivated. All right, this is all like simultaneous, but you get a callback function to do this transition smoothly. Your audio becomes deactivated. The phone call audio session terminates, becomes deactivated, and then your audio session becomes activated again until the user turns it off. So how do we handle this? First thing we need to do, and we'll do this in the setup somewhere or in our init, is we want to ask the notification center for the default center. So default center is a class method that we can call on NS notification center. It'll give us a pointer to the default center, and we can add ourselves as a delegate. Okay, so we're going to add self as an observer. We get to pass the selector, right? Remember, selector just means function. We get to pass the selector that we want to be called. So we're going to make a new function called handle interruption. We're going to say when an interruption happens, I want you to call this function right here, and the notification center will do that. And this is for an AVAudio interruption notification, right? And the object that is making this call is session, right? Right back here, we already have a copy of session here. So we're just passing that in as the object making the call. So if the AVAudio session is about to notify you that an interruption is about to happen, then it will call handle interruption. So we should fill that out. We get a notification here, which we can grab some information from. So the first thing we're going to do is we're going to grab from the notification user info the interruption type. Okay, and this is just going to be a number, but this number is enumerated, so we can either check to see whether it's a begin type or an end type. So in other words, the interruption is about to happen or the interruption finished happening. And depending on the case, we can fill out different different commands. So if the interruption is about to happen, we might want to pause the audio, and then when the interruption is ended, we might want to automatically resume the audio. So this makes for a really nice user interface. Okay, it's pretty simple though. We fill out one function and we register for notifications. It's that simple. Now our app is playing nicely with other audio that's going on. One slight caveat to be aware of. Now this is actually a little bit out of date. Let's change this. This was not fixed in iOS 10. So, starting with iOS 9, you were not guaranteed an end interrupt method once the start interrupt method was called. Okay, it wasn't being reliably made. And even from the Apple documentation, it says specifically, there is no guarantee a begin interruption will have an end interruption. So this can be annoying. If you, for example, inside your begin interruption, you pause your audio, that seems like a typical thing to do. You'd like to be able to automatically resume the audio. Won't necessarily happen. I haven't seen any updates since September 2017, but I did see this. You can find it right here actually in the notes. You can go here to this documentation. It says it was updated September 2017, and it still had this warning. So apparently this has not been fixed yet. Okay. Other audio session properties. So this gets a little bit to more the nitty-gritty of your specific needs for your app as opposed to interacting with other apps. So you can specify your preferred hardware settings, including the sample rate and the preferred I/O buffer size. So for example, in our AVAudioEngine, you can init with the buffer size, right? We're using N equals 1024. You may as well go ahead and let Core Audio know that that's the buffer size that you want, instead of just getting whatever buffer size it defaults to. And you can specify your preferred sampling rate. You can also query the hardware characteristics, so you can get the I/O latency, the I/O channel counts, whether there's a microphone available or not. I actually ran into this problem on one of my computers running one of our AV audio players. I was using a sound card that did not have a microphone enabled, and I was trying to access the microphone, and it kept crashing, and I wasn't getting a good crash report. It compiled and built just fine, but as soon as I went into the simulator, it would crash. If I had set up an audio session and checked first for the availability of a microphone, I would have seen right away that accessing the mic would not work. So it's a good thing to do. And you can check and see what the volume settings and the sample rate are as well. And then the third thing we talked about already in depth was responding to device notifications. So these are all easy properties to set. In order to set the sample rate, you just call set preferred sample rate on audio session, right? To set the preferred buffer duration, you need to figure it out in seconds, which is a little bit annoying. So you take your frame size divided by your sample rate, right? And you save that as an NS time interval, right? This is not a float, this is an NS type. But you can just pass that buffer duration to your session via the set preferred I/O buffer duration selector. Or for, instead of one of the setters, if you want to get, for example, the hardware's sample rate, you just call current hardware sample rate on session. So that's the end of this slideshow. Let's just jump over to some code real quick and look at how we set up a session in this project. Pretty quick here. First thing we're going to do is we're going to call this shared instance creator on AV audio session. This is a class method, and it's going to return a singleton object, a pointer to a singleton object called session of type AV audio session. We'll go ahead and set up some variables for dealing with errors. So the first thing we're going to do is set our category to an AV audio session play and record category. Okay. If that fails, we'll just print out a little message to the log that there was some problem. Next thing we want to do is we want to set our preferred sample rate. Right? We need this. We need the system sample rate to match what our coefficient calculator sample rate is. If there's a mismatch, then our frequency, our center frequency FC, is going to be mismatched. Right? It's not going to match. It's not going to be what we think it is. So we need to make sure our sample rates match. We want to set our preferred I/O buffer duration. This is again comes from the buffer size that we're using for our FFT. All right, this is our audio frame size. Again, we have to scale it by, normalize it by the sample rate so that we get this in a time, right? And lastly, we want to set our audio session as active. We're ready to start playing audio, right? We're loading in, here we're loading in a file what you're doing is you're accessing from the microphone, but in either case we want our session to be active. Okay, so that's it. I think we've gone through every line of code in this project. I think you understand it all, and I'm looking forward to seeing your presentations on Tuesday. So email me with questions. I have some time to answer emails, and good luck on your App 3s, and I'll see you next week.